The J programming language, developed in the early 1990s by Kenneth E.Iverson and Roger Huey, is a synthesis of APL and the ER and FL function-level languages created by John Backus. To avoid repeating the APL special character problem, J requires only the basic ASCII character set, resorting to the use of the dot and colon as inflections to form short words similar to digraphs. Most such primary J words serve as mathematical symbols, with the dot or colon extending the meaning of the basic characters available. Additionally, many characters which might need to be balanced in other languages are treated by J as standalone words or, when inflected, as single-character roots of multi-character words. J is a very terse array programming language, and is most suited to mathematical and statistical programming, especially when performing operations on matrices. It has also been used in extreme programming and network performance analysis. Like the original FL languages, J supports function-level programming via its tacit programming features. Unlike most languages that support object-oriented programming, J's flexible hierarchical namespace scheme can be effectively used as a framework for both class-based and prototype-based object-oriented programming. Since March 2011, J is free and open-source software under the GPL v3 license. One may also purchase source for commercial use under a negotiated license. Examples: J permits point-free style and function composition. Thus, its programs can be very terse and are considered difficult to read by some programmers. The Hello World program in J is Hello World. This implementation of Hello World reflects the traditional use of J. Programs are entered into a J interpreter session, and the results of expressions are displayed. It's also possible to arrange for J scripts to be executed as standalone programs. Here's how this might look on a Unix system. #bin JC echo hello world exit. Historically, APL used to indicate the fold, so +1 2 3 was equivalent to 1 + 2 + 3. Meanwhile, division was represented with the classic mathematical division symbol, which was implemented by overstriking a minus sign and a colon. Because ASCII in general does not support overstrikes in a device-independent way, and does not include a division symbol per se, J uses % to represent division, as a visual approximation or reminder. The following defines a J function named AVG to calculate the average of a list of numbers. AVG equals plus %#. This is a test execution of the function. AVG12342.5 counts the number of items in the array, plus sums the items of the array. % divides the sum by the number of items. Note: AVG is defined above using a train of three verbs known as a fork. Specifically, NY is the same as V1, which shows some of the power of J. Some examples of using AVG: V equals $2,100 NB. A random vector V46557954396094185192786090609062 AVG V59.24 AVG VNB. Moving average on periods of size 4, 5, 8, 60, 5, 6, 51.25, 52.5, 54, 67.75, 64.25, 69.5, 57.75, 38.75, 40, 43.5, 59.75, 70.25, 80, 72.5 meters equals 45, $50 NB. A random matrix M4652924239104446281318142228104012 AVG 1 meter NB. Apply AVG to each rank 1 subarray of M17.2, 22, 21.2, 26.4. Rank is a crucial concept in J. Its significance in J is similar to the significance of select in SQL and of while in C. Here is an implementation of quicksort from the J dictionary. Cell equals adverb def u hash quicksort equals verb define if 1 greater than hash y do y else quicksort y greater than cell e equals y tilde hash y end. The following is an implementation of quicksort demonstrating tacit programming. Tacit programming involves composing functions together and not referring explicitly to any variables. J's support for forks and hooks dictates rules on how arguments applied to this function will be applied to its component functions. Quicksort equals $angry face, caret. Sorting in J is usually accomplished using the built-in verbs and user-defined sort such as quicksort above, typically are for illustration only. The following expression exhibits by with n digits and demonstrates the extended precision capabilities of J. N equals 50 NB. Set n as the number of digits required less than atto 10x caret NNB. Extended precision 10 to the nth asterisk pi
314159263846643327950288419716939393751. Data types and structures. J supports 3 simple types: numeric, literal, boxed. If these, numeric has the most variance. One of J's numeric types is the bit. There are 2-bit values, 0 and 1. Additionally, bits can be formed into lists. For example, 10101100 is a list of 8 bits. Syntactically, the J parser treats that as a single word. Lists of arbitrary length are supported. Furthermore, J supports all the usual binary operations on these lists, such as or, exclusive or, rotate, shift, not, etc. For example, 1001010 plus 01011010 NB, or 1101101003. 10110011111 NB. Rotate 100111111. Note that J also supports higher order arrays of bits. They can be formed into 2-dimensional, 3-dimensional, etc. arrays. The above operations perform equally well on these arrays. Other numeric types include integer, floating point, complex, extended precision integer, and rational fraction. As with bits, these can be formed into lists or arbitrarily dimensioned arrays. As with bits, operations are performed on all numbers in an array. Lists of bits can be converted to integer using the hash verb. Integers can be converted to lists of bits using the hash verb and a word form in characters. They're never tokens by themselves unless preceded by white space. J also supports the literal type. Literals are enclosed in quotes, for example, A or B. Lists of literals are also supported using the usual convention of putting multiple characters in quotes, such as A, B, C, D, E, F, G. Typically, individual literals are 8 bits wide, but J also supports other literals. Numeric and Boolean operations are not supported on literals, but collection-oriented operations are supported. Finally, there's the box data type. Typically, data is put in a box using the less than operation. This is analogous to season operation. However, where the result of season has reference semantics, the result of J's less than has value semantics. In other words, less than is a function and it produces a result.
The result has 0 dimensions, regardless of the structure of the contained data. From the viewpoint of a J programmer, less than puts the data into a box, and lets the programmer work with an array of boxes. Less than 10010 plus 10010 plus. The only collection type offered by J is the arbitrarily dimensioned array. Most algorithms can be expressed very concisely using operations on these arrays. J's arrays are homogeneously typed. For example, the list 1, 2, 3 is a list of integers, despite the fact that 1 is a bit. For the most part, these sorts of type issues are transparent to the programmer. Only certain specialized operations reveal differences in type. For example, the list 1.00.01.00.0 would be treated exactly the same, by most operations, as the list 1010. J also supports sparse numeric arrays where non-zero values are stored with their indices. This is an efficient mechanism where relatively few values are non-zero. J also supports objects and classes, but these are an artifact of the way things are named, and are not data types in and of themselves. Instead, boxed literals are used to refer to objects. J data has value semantics, but objects and classes need reference semantics. Another pseudotype, associated with name rather than value, is the memory-mapped file. Documentation. J's documentation includes a dictionary, with words in J identified as nouns, verbs, adverbs, conjunctions, and so on. Primary words are listed in the vocabulary, in which their respective parts of speech are indicated using markup. Note that verbs have two forms, monadic and dyadic. For example, in -1, the hyphen is a monadic verb, and in 3-2, the hyphen is a dyadic verb. The monadic definition is mostly independent of the dyadic definition, regardless of whether the verb is a primitive verb or a derived verb. Control structures. J provides control structures similar to other procedural languages. Prominent control words in each category include assert, break, continue, for, go to _ label, if, else, else if, return, select, case, throw, try, catch, while, whilst.